All right, good deal. So, real quick, I'm going to open up the chat. And does everybody see the question that I just put up there for you guys? So what was the last unit you worked on in your pre-calculus class? All right, so we've got some logarithms, we've got some intro to trig identities, more logarithms. All right, cool. So what we're going to work on today is all about vectors, and vectors are one of the later units that you see in pre-calculus, but I wanted to go over it today because it's something that you're going to see, or that you're not really going to see in school since we're going to be out of school for a little bit. But it's something if you take a physics class or anything like that, you're going to use vectors a lot. So we've got somebody else wanting to join in. So let's go over this problem here. In the chat, or I guess I'll do it right here for us. Let me go ahead and start annotating this. This is a 45, 45, 90 triangle. So we know that this is a 90-degree angle. We know that this is 45 degrees, which means that this angle also has to be 45 degrees. We know if this is 12, we can use our properties of special right triangles. We can solve the other sides. This should equal 12, and C should equal 12 root 2. If you didn't use special right triangles, you can use sine and cosine using the unit circle, or you can also do, if you knew that, properties of isosceles triangles, if this angle's 45 and this angle's 45, it's not a straight line, we know that these two sides have to be the same. And then from there, we can do the Pythagorean theorem. So lots of different ways we can solve this problem, all right? Now we're gonna go ahead and get started on our vector seminar. So think about vectors. I know a lot of you guys haven't heard of vectors before. You're used to seeing scalars, which is a physical quality described by a number in a unit. So things like 5 miles or weights in grams or degrees in Celsius, pretty much anything with a unit. The thing about scalars is that they don't have a direction, whereas vectors do have a direction. They have a magnitude and a direction. So that word magnitude just means size. It's going to be the length of our line. So a little bit more specifically, we can say vectors are things like 5 miles east, where we have that magnitude, that 5 miles, and that direction, east, or this 80 kilometers per hour, southwest, that magnitude in that direction. What we're going to be working a lot with today is velocity. Well, I'm going to try, I don't know how to get rid of this thing down here. Guess we'll just have to deal with it. It might be in the way a little bit today, but that's okay. All right, so vectors, we can represent them a couple different ways. The first way is using arrows. Let me actually use this. All right, so you can kind of see my pointer here. So we've got an arrow here. This would be a vector that's facing east. It's fairly small in comparison with these two vectors over here. Now, something I want to point out with these vectors is that they have directionality. So these two vectors are parallel, meaning they're going in the same kind of direction, or they have the same angle. The big difference is where the arrow is. So see on this angle here, or this vector here, the arrow is down here versus up here. The arrow is at the top here. That's a big difference. So really they're parallel, so they look like they should have the same angle, but these vectors are going to be drastically different in their angles when we do them mathematically. And then the big difference between these two are the size. So the magnitude or the length. So the length is going to be proportional to the magnitude. We'll get into that a little bit more in just a second. So that's graphically. We can also use symbols. And so if we have vector RS, which is kind of down here, I don't know what you guys are seeing, but if you have the little video screen over here or up top, you can go to view options and kind of hide all the thumbnails. All right. So we've got this vector here, RS. There's a couple important things about this. So RS here, we have this arrow on top. Now we can't label this vector as vector SR down here for a couple reasons. The first being that it's in the wrong order. R is our initial point, which is where the vector starts, and S is our terminal point where the vector ends. So R has to come first and S has to come last, and the arrow has to always be pointing to the right. So we can't have the arrow pointing to the left, and then we also can't have it in this opposite order here. All right, so far, anybody wants to put it in the chat. Does anybody have any questions just about some of the basics that we've been over? I'll give you a second to type those. All right, so it looks like no questions so far. Awesome. Oh, go back to the first screen. Let's see, Erin. Are you saying this first screen? Let's see. All right, Erin, I'm gonna leave this up for about 30 more seconds and then we're gonna kind of go on to where we left off. All right, so let's see. Okay, so the other thing that I want to talk about is vectors being about displacement, not position. So if we look at this vector here, I've got my initial point R at 3, 6, and my terminal point S at 7, 1, right here. So if I were to label this vector, and I wanted to put it, if I wanted to give a name to this vector, I could call it vector RS. There's two ways that I can write vector RS. The first one is component form. And we're going to break this down in kind of our X component and our Y component, kind of like a coordinate pair. The only difference is that we're going to use these kind of pointed parentheses, basically the less than and greater than signs. Just think of them as pointed parentheses. The other way is this linear combination form. This is something you'll see a little bit more often in physics, not as much in pre-calculus, but it is something I wanted to mention. So let me write on this real quick. So to find my component form, what I'm going to do is I'm going to treat R kind of like the origin. And from here, I see that to get to S, ooh, that's not a straight line. I have to go down 1, 2, 3, 4, 5 units and over 1, 2, 3, 4 units. So if I were to put that in component form, I would have 4, -5, or in linear combination form, 4i minus 5j. Here, I just represents like our x value and j just represents our y value. Notice that 5 is negative, so it's minus 5j. Any questions on component form or linear combination form, go ahead and put those into the group chat for me. All right, looks like we're good. So we're going to go ahead and go on. Oh, let me clear out my drawings. So now we're going to talk a little bit more about magnitude. So I mentioned earlier magnitude was the size or the length of the vector. So I've got this vector here, and I need to find the magnitude. Now, something to note, magnitude is never going to be negative. It's kind of like absolute value. If we're going 5 miles an hour, we're not going 5 miles an hour negative. We can go 5 miles an hour south, which could be negative, but the unit itself is never negative. So if we want to find the magnitude of our vector v here, we'll represent that as, you see these two kind of lines. It looks like double absolute value. You'll see this is, that's how we represent magnitude. Occasionally you'll see it as the absolute value. That's kind of just a formatting thing on worksheets, but really it should be this double absolute value symbol. And the way that we find the magnitude is really just the Pythagorean theorem or the distance formula. So if I look at this problem here, I'm going to go ahead and just draw, I'm going to make this a right triangle. And I see that my bottom here is 8, and my other leg here is 5. So I can do the Pythagorean theorem, 8 squared plus 5 squared equals c squared. Jump up here. I'm going to go ahead and say c is the square root of 89. So that's my magnitude. Is that? Oh, I wrote over here. So kind of skip this step here. So let me clear out some of what I wrote. So component form, that's kind of what we found earlier. We just didn't put it in component form. So this component form is, again, basically our change in our x values, which is 8. And then our change in our y values, which is 5. And then the magnitude of v, the Pythagorean theorem, which we just did, to get the square root of 89. All right, now the other thing that vectors have is a direction. So there's a couple different ways that we can measure direction. This can be a little bit tricky, so we're going to definitely stop for questions after this. And we think we've got a couple practice problems after this as well. So we can measure counterclockwise from the positive x-axis, just like the unit circle. So just like you've seen before in trigonometry. So say if I have this right here, you would say this angle, it's not exactly 45 degrees, but it's pretty close, would be 45 degrees. So this would be, the direction would just be 45 degrees. Now we're going to see this a lot. The other thing that we're going to see is bearing. And this we're going to see a lot of in applications. So 2 ways that you'll see bearing represented. You'll see clockwise from north. So this one's a little bit different. Let me put my directions on here. So if I have 80 degrees, what that's going to look like, actually something more like this, because we're going clockwise from north. So we start at north and then go 80 degrees this way. Now 80 degrees from north, we could say that the bearing is 80 degrees, but the direction is 10 degrees. Does that make sense to everybody so far? Now the other way that we'll see bearing, take this off, is this weird format right here. And so we have S, 43 degrees, and E. The way that we say that out loud is 43 degrees east of south. And really what that means is that we're going to start with our first direction here. We're going to go south, and then we're going to go east by 43 degrees. All right, so this would be 43 degrees east of south. So those are the two ways to see bearings. Does anybody want any clarification on that? Go ahead and put that in the Zoom group chat. Give you about 30 seconds. All right, the second part of bearings, yes. So let me take this off. So somebody wants us to go over this bearings part 2, this guy right here again. This one is quite confusing, and we're actually going to come across a problem like this later. So we're always going to start, this is kind of our initial direction, this south. So we're going to go south first. Highlight that. And then our second direction is east. So from south, we are going to go east, towards east, which is going to be that direction there. All right, and that we're going to go that direction by 43 degrees. There's my vector with a bearing of 43 degrees east of south. Kind of a weird way to say it, but just focus on the fact that you're going to do the first letter, you're going to go there first, and then the second letter, the letter that comes last, that's the direction you go from that original south. Does that like make a little more sense? All right, good deal. I'm going to go on to the next slide here. So this one's kind of a practice problem, all about finding direction. And so again, what we're going to do, draw on this, I'm going to use green. So vectors are all about displacement. So I'm going to treat my vector kind of like this is my new origin, the initial point and the terminal point. The initial point, I'm going to treat that like the origin. And I'm going to draw a right triangle here. And I see that my x component is going to be 1, 2, 3, 4, 5. And my y component is going to be 3. So with this, I can use tangent. So if everybody has their calculators and they want to do this with me, what I'm going to plug into my calculator is tangent inverse of my y value, 3, over my x value, 5. Now make sure you are in degrees for this. We don't want to do radians. I know a lot of your pre-calculus class is in radians, but this is one of the things that is in degrees. When you do this, let me do it on my calculator too. Tangent inverse. You should get 30, we'll go to 2 decimal places. So 30.96 degrees, all right? So that would be the direction, is 30.96 degrees. And that's this angle right here. Now, if I wanted to find the bearing, the first way we did it, remember, was clockwise from north. So there's my north. Clockwise from north is going to go this way. So for that, I can just do 90 minus that angle. And I will get 59.04, and that's my bearing clockwise from north. All right, now the other option is I can do it based on compass heading. So I'll do this one in a different color as well. So with this one, we're actually going to keep the answer, this 59.04. Now we just have to figure out the letters that go with it, which is the tough part. So generally your first is going to be either north or south. In this case, we went north first, so that's the first letter that's going to come up. And then from there, we went to the right, which is east. Let me put my degree sign here. So this is 59.04 degrees east of north, where the N comes first and the E comes second. Does everybody understand that one? Go ahead and put your, if you have any questions, go ahead and put that in the group chat. All right, looks like we are good. So I already asked for questions. Does anybody have any questions that you want to go back and review anything from earlier? All right, so we've got two practice problems here. This first one, we're not going to use a calculator. We should be able to do a unit circle. What I'm going to do is I'm going to give everybody, we'll say 3 minutes to get this, this problem started, and then we'll jump in and do it together. So I'm going to put a timer for 3 minutes up. All right, everybody's got about a minute left, and then we'll get started on this problem. If you by chance already have the answer and you want to try it, you can send a chat to me, and I just want your answer in component form. If anybody wants to take a stab at it before we go over it together. right, so it's been about 3 minutes. We'll go ahead and get started going over this problem. So the first thing that I'm going to do is I'm going to draw a picture. So we've got a magnitude of 15 feet. Actually, here, I'm going to do this. I forgot I can draw lines. Okay, so this magnitude of 15 really just represents the hypotenuse, or the length of this vector. I have my arrow here because that's important. And we know it's at a direction of 30 degrees. So it's a direction, so it's from the positive x-axis counterclockwise, just like we're used to in most of the trigonometry we've already seen. So what I need to find is the x component of my vector and the y component of my vector. And I can do that by just using sine and cosine. So to find my x component, I guess, yeah, we'll do the x component first. I'm going to do cosine of 30. And we know that cosine is equal to adjacent over hypotenuse. And in this case, our hypotenuse is 15. So I can go ahead and solve this out. The rest of this isn't going to be nice and pretty typed, but we can do it. So we have 15 times the cosine of 30. And that's my adjacent, or I'm going to go ahead and say that that's the x component. And I know that the cosine of 30 is root 3 over 2, so I'm going to have 15 times root 3 over 2, and I'm just going to leave it as the x component, 15 root 3 over 2. All right, now I'm going to do my y component. For my y component, I can just do sine of 30, which is going to be equal to my opposite over my hypotenuse, which is 15. Hello, sorry. So then I can solve this. I'm going to say 15 sine 30 equals my opposite, which is my y component of my vector A. The sine of 30 is 1/2. So I'm going to get 15 over 2. So that's in component form. Now, if I wanted it in linear combination form, what I can do is I can just put my x coordinates, so my 15 root 3 over 2, and that's going to be followed by I, plus my y component, 15 over 2, and j. All right. Does anybody have any questions over this first practice problem? You do just type yes, so I know we can wait a second for you to type the rest of your question. And if not, we'll head on to the next problem. All right, so it doesn't look like any of you guys have any questions on this problem, so I'm going to go ahead and clear this out. And we will go on to the next one. So this one we can use the calculator for, so hopefully you guys have your graphing calculators with you, or just any calculator that will do sine and cosine and tangent. And we've got 2 points that we want to create a vector in between those, so vector GH, and we want to find both the magnitude and the direction. So we'll give everybody another 3 minutes, and then we will get started on this problem together. All right, so everybody has about a minute left. If anybody's gotten the answer to the first part or the second part and they want to type it in the group chat just to see if you've gotten it right, feel free to go ahead and do so. We'll go over it in about a minute. All right, I see nobody's feeling bold and nobody wants to put their answer in the group chat. That's okay, we'll go over this question here. So first thing I'm gonna do is I'm gonna plot my 2 points. So I've got G at 0, -4. I've got H at -6, 3 here. So again, vectors have directionality where G is gonna be my initial point, and H is gonna be my terminal point. So there's my vector, and I need to find the magnitude. I'm gonna first start by making this a right triangle. And I'm just gonna do the Pythagorean theorem. So I see the bottom is 6, and the other leg here is 7. So I'm gonna do the Pythagorean theorem here. C squared equals 6 squared plus 7 squared. And take the square root of both sides to get the square root of 85. So my magnitude is the square root of 85. I could plug that in my calculator and get some sort of decimal. I'm not going to, just because I like it in the radical form a little bit better. And the other thing I need to do is find the direction of GH. Now this one's a little bit tricky because, again, direction is measured from the positive x-axis. So if I kind of redraw my coordinate system here, so that my initial point is like my origin, the angle that I'm looking for is this angle right here. But if I use inverse tangent, I am going to be given this angle right here. So I'm gonna have to do a little bit of extra work, but that's okay. So we'll go ahead and find the blue angle. So I'll say tangent inverse, that's a big one, of opposite over hypotenuse. So it's gonna be 7 over 6. I plug that into my calculator. Again, I want everybody's calculator to be in degrees, not in radians. I should get an angle of 49. We'll just round that to 1 decimal place. 49.4 degrees. All right. But again, that is this angle right here. And direction is always measured from the positive x-axis. So I am going to very simply do 180 minus 49.4, get 130.6. So the direction of GH is 130.6 degrees. Now, if it had asked for a bearing, I would find it from north to that angle, or I could say well, that's probably what I would do. I wouldn't do it any other way. All right, any questions on that? If you have a question, just type yes into the chat box so I know to wait while you type up the rest of your question. If not, we will go on to the next slide in just a second. All right, I don't see any yeses in the chat box, which means it is safe for us to move on. So we'll go ahead and move on to our next slide here. Our next slide covers something pretty important. It's called the unit vector. So if we think about the unit circle, it's got that important unit in there, and unit means one. So a unit vector is just a vector with a magnitude of 1 and the same direction as a given vector. So really what we're going to do is we're just going to follow this formula here. And this needs brackets here. So in order to find the unit vector, I'm just going to take each of my components, my x component and my y component, and divide each of those by the magnitude. So I've kind of already worked through this problem a little bit here, but we'll go ahead and do this one together too. So I've got point A at 0, 3, and B at -1, -2. So I'm going to show my directionality with an arrow. Now, very clearly, this has a magnitude of greater than 1. We're going to go ahead and find that magnitude by doing the Pythagorean theorem. I'm going to turn this into a right triangle. And I see that my base is 1, my height, that's not a 5, is 5. So if I were to write vector AB in component form, we should do that first. I would say -1, -5. Now they're both negative because if I take my initial point and treat that like the new origin, I'm going to the left and I'm going down. So both of these are in fact negative. And I'm going to go ahead and do the Pythagorean theorem. So 1 squared plus 5 squared equals c squared. I'm going to get c is the square root of 26. So that's my magnitude here, is the square root of 26. So to find the unit vector, I'm going to take my x component right here, -1, and divide it by the square root of 26. I'm going to take my y component, my -5, divide that by the square root of 26. Now this answer is okay. It's not great because I've got a square root in the bottom, so I would want to rationalize that to get -1 root 26 over 26 and -5 root 26 over 26. So this would be the component form of my unit vector. Any questions on unit vectors? Again, just type yes into the chat box so I know to wait while you type up the rest of your question. All right, looks like no questions here, so I'm going to go ahead and clear this out. We will go on to the next one. So the next kind of portion of this is vector operations. So we're going to bring back scalars and talk a little bit more about scalars and how we can multiply scalars times vectors. We're going to do some vector addition and some vector subtraction, and then we're going to get in some vector applications. So first we've got scalar, and remember a scalar is a quantity with magnitude but no direction. And get my pencil out. I've got this vector here, DC. So DC is 4, -3. So it's my component form. So I'm going to go 4, -3. Here's my vector DC. And I want to find 2DC. So really what that is I'm just going to take this, I'm going to multiply it by 2. So I can go 1, 2, 3, 4, 1, 2. I can go twice that distance. And 2DC would be the whole thing here. All right. Now I can also do that algebraically fairly easy. What I'm going to do, so I'm going to just take each of my components and multiply those. I think I actually might have typed this out. Let's see. Oh, nope, I didn't. So let me go back real quick. All right, so to find 2DC, what I'm going to do, so I'm going to take my x component, 4, and multiply it by 2, and take my y component, -3, and multiply it by 2. So my 2DC is going to be 8, -6, and I can confirm that by taking a look at this vector. It has an x component of 8 and a y component of -6. So scalar multiplication, pretty easy. You can do it graphically or you can do it algebraically like we did over here. Let's see, we've got a question. So if we distribute the 2 to both of them, yes, and what if there are 3 vectors? So we'll actually, I think we'll come across, I don't remember if there's one with 3 vectors here. Really what you would see with an example, like 3 vectors would be something like this. So you would see like 3, there we go. So if you had 3 vectors, we'll actually kind of talk about this in a minute. You would kind of do that same process here where you would multiply here, and then you would add these vectors in, which we're about to talk about in just a second. Does that kind of help answer your question a little bit? I know it's kind of a weird. Okay. We will go ahead and move on to vector addition. So with vector addition, the name of the game here is tip to tail. So with this, I'm going to have vector R, 3, 1, which is over here. So I've got my x component 3, my y component 1, and then I have my vector S, which is going to be -2, 4, so my x component -2, my y component 4, and I want to add those together. All right, so the way that I'm going to do that graphically is I'm just going to take this red vector, or this second vector, and I am going to slide it over here. So we're going to have R plus S. And remember how we talked about vectors are always about displacement? So my resulting vector is going to go from the origin to where I ended up, the tip of S. Now, there's something called the parallelogram rule. It kind of, if everybody thinks about some of the properties of addition, the order that you add doesn't really matter. And the same goes for vectors. So R plus S and S plus R are going to give me the same thing. So over here, this is R plus S. This left side over here is S plus R, where I have S and R. And I still end up at this point right here. So my resulting vector being 1, 5. That makes sense to everybody so far. Okay. Now, that's how we do it graphically. We can also do it algebraically, which a lot of you guys might prefer. So we're going to break it down into component form, and we're just going to add the x components and we're going to add the y components. The trick here is that you never want to add x and y. You only want to add x's to x's and y's to y's, kind of like combining like terms. So for my r, I have 3, 1. So I've got my x component here, my y component here. And s, I have -2, 4. Got -2, 4. So I'm going to have 3 plus -2 to give me 1, and 1 plus 4 to give me 5. End up with the same vector 1, 5 in component form. All right, so that's vector addition. Now vector subtraction, we're actually going to do something very similar. The only difference is if we think about like subtracting integers, a lot of times we just add the opposite or add the negative of that. So we're going to do the same thing. So, oh, this shouldn't be here yet. So we have the same vectors here, vector r and vector s, but now instead of adding, we are going to subtract them. So we have r minus s, or I'm going to think of it as r plus -s. Now we first have to figure out what -s is. And -s is just going to be, it's kind of like distributing a negative. We're going to change the sign on 2, change the sign on 4, so we're going to get 2, -4. Now you can see my positive s here and my -s here. They make a line. So we're just kind of reflect it into the opposite quadrant. And then we're just going to do components here. So as you can see, to add this, I'm going to do r plus s, or I guess we'll do it graphically as well. So I'm going to take this s vector and slide it over here so that it's tip to tail. And my resulting vector, again, from the initial point to where I end up, I'm going to call that vector q. And let's see, let's see. Yeah, you guys can't see that on your screen, can you? Okay, so I'm going to try not to move this so that the little thing goes away. But so you can see the components form here. I've put them 2 different ways. The first one being r minus s, the second one being r plus -s. You can think of it either way. You'll get the same answer whether you do r minus s or r plus -s. Any questions on vector addition or vector subtraction or scalar multiplication? All right, it looks like we are good there. So nobody has any more questions. We've got a couple practice problems to do. And this one, we are going to use the calculator for. This one's kind of a tough one. We have to be really careful of this angle here. So that's my hint that I'm going to give to you guys. I'm going to give everybody another 3 minutes to see if you can figure it out on your own. All right, everybody's got about a minute left. This one is a little bit of a longer problem, so you may not be able to finish this one, but we'll start going over it in a minute. All right, so we've got two vectors here and we want to add them together. So we're going to talk about doing it a little bit graphically and then also do it in component form. So first thing I'm going to do is draw vector u. So I see that vector u has a magnitude of 25 and a direction of 29 degrees. So I'm just going to say that's probably going to ignore the numbers on our graph here because I'm not sure that this is the right scale, but we'll say that that's 29 degrees and that our magnitude is 25, and that's vector u. Okay, now our other vector, vector v, has a magnitude of 25 and a direction of 222 degrees. Now 222 is going to be down in this third quadrant here. This is 222 degrees. This also has a magnitude of 25. So if I were to add these, oh, I'm doing negative u plus v. So let's actually find negative u first. So let me go back to pink. I am going to turn my vector u into a right triangle here. And again, we're ignoring these numbers on the bottom. Okay, I'll do this. We'll write it down here. So there's 25. There's my vector. Here's my 29 degrees. And my right triangle here. So to find, oh, this is not vector A. This is the y component. I am going to set up sine of 29 degrees equals my opposite, which is my y component, over my hypotenuse, 25. I can solve this. This is going to be 25 times the sine of 29 degrees. And this should be 12.12. To find the x component, I'm going to set up cosine. Of 29 degrees equals adjacent, or my x component, over my hypotenuse, 25. I can solve that for 25 times the cosine of 29 equals my x component. So my x component should be 21.87. All right, so I'm gonna go ahead and I'm gonna write that up here, kind of put it out of the way. Oh, and I need to make it negative. So I'm gonna distribute that negative in, again, that scalar multiplication. This will become negative 21.87. And my y component, negative 12.12. All right, so that is negative vector u. All right, now I need to worry about my vector v. I'm going to find the components of my vector v. Now, something a little special with this is that I'm working in the third quadrant, so my angle isn't quite what I'm used to. Ugh. So here's my third quadrant. Here's my vector. Go ahead and make that a right triangle there. Now, I know that this angle is 222 degrees. So to find the angle within my triangle, I can do 222, take away 180, and I will find that my angle that I'm going to be working with inside my triangle should be 42. Right, and the magnitude for this is 25, same as the last one. So I'm going to go ahead and find the components of this. Now, we can say, for this one, we'll do x first. I know I did y first on the last one, but we'll go ahead and set up cosine of 42 equals adjacent. So this is, oh, forgot to label my vector. This is vector v is the x component of my vector over 25. So I can solve and say 25 times the cosine of 42 gives me the x component of my vector. If I solve that, I should get 16.73. Now, if we go back and think, we're in the third quadrant here, so we know cosine values have to be negative. Now, this is kind of where our calculator doesn't really help us a whole lot. So I'm going to make sure that I remember that's negative. Let's see, so why did we use 42 degrees instead of 222 degrees? So 222 degrees, I guess I could plug that in my calculator. I prefer to use 42 because that's what's inside of my triangle. 222 is from the positive x-axis. Does that answer your question? Oh, I cut out. Okay, so I'll explain it again. So the 222 degrees is from the positive x-axis. That's a lot of angle to work with. I just want to work with the angle that's inside my little triangle here that I created with my vector. So I did 222 minus 180 to get that 42 inside. Okay, good, perfect. All right, so that's the x component of my vector for vector v. Now I need to find the y component. So my y component, I'm going to set up sine of 42 degrees equals the y component of my vector over 25, which I will solve. Oh no, and I'm running out of room. So 25 sine of 42 equals the y component of my vector. And for this, I got, oh, nope, that's not it. 18.59. And again, I know I'm in the third quadrant, so my y coordinate should mean negative as well. I'm going to go ahead and put that up here. V is negative 16.73 for my x component. The comma went a little wild there. And negative 18.59 for my y component. Now back to the very original question, I need to find negative u plus v So I just need to add my x components and my y components together. Let me make some room down here for us. So to do my negative u plus v, I'm just going to, oh, that's not what I want. Add my x components together and get negative 21.87 plus negative 16.73. Negative 38.6. And then my y components, I add those together. Negative 12.12 plus negative 18.59 to get negative 30.71 for that. And I see we've got a question there. So my cosine and sine were flipped when I was finding v. I found the right values, just swapped. So for, I guess for v, you got this negative 18, you got that for your x coordinate and negative 16 as your y coordinate. Did anybody else get that? Okay, so let's see, what what angle did you plug in for when you plugged it into your calculator? Did you plug in 42? All right, let's see, I did this in my head, so I might have made a mistake here. Let me work it out real quick. Oh, you know what? You are totally right. Yep. So scratch that. Let me. Nope, that's not what I wanted. Okay. My bad, you guys. Okay, so it's the other way around. Thank you for pointing that out, Emma. All right. Now we'll add our x and y components together. I'm not going to write it out. I'm just going to solve for it. So the x component, negative 40.46. And negative 28.85. There we go. So that's my x component, and that's my y component. All right, any questions on that one? All right, doesn't look like that. If there's any question. Thank you again for pointing that out, Emma. My bad. All right, so practice problem 4. So with this one, this is the last problem before we get into some applications. Oh, Here we go. So again, I will give everybody about 3 minutes to do this problem. And we will check in after that. While you guys are working on it on your own, I'm going to start plotting some of these points here. All right, we've got about a minute left. If anybody's already solved this problem and they want to put their answer in the chat, go ahead. If not, we'll get started in a minute. Alrighty, so the first thing that we want to do is, well, I plotted my vector AB and my vector CD. Now I won't do this one graphically because I don't have enough room on my graph here. So we'll just do it in component form. But the first thing I need to do is find my component form. So with my vector AB, again, we're talking displacement here. So if A is my new origin, I can see that that the components of my vector A are -7, -1. And same thing with C. I'm going to make C kind of my new origin and find the components there, and that is going to be 3, 2. So then algebraically, I kind of just need to follow the directions here. So I'm doing -3AB. That's some scalar multiplication in there. So I'm going to multiply each of my components by -3. I'll have 21 and 3. And then I need 2 CD. So some vector multiplication or some scalar multiplication there. I am going to get 6 and 4 for my components. And then to add those two together, I'll add my x values, or my x components, and my y components to get 27, 7. How did I get 7, -1? Oh, -7, -1. So we are looking over here. So vector A, again, we have A at 10, 0 and B at 3, -1. So we've got vector AB here. If I make A my initial point and kind of treat that like the origin, I see that I go over 7 and down 1. So that component form is -7, -1. Does that make sense? Yes, vectors are all about right triangles. That's the kind of foundation for all of this is right triangle trigonometry. Any other questions on this problem here? All right. So next we're going to talk some vector applications and some vector word problems. So there's a couple here, and the first that I want to start with is this problem right here, which is actually from a released pre-calculus exam. I believe it's from the 2015 exam. I know there's a note in there at some point in a second, but let's take a look. So we have a wind that is blowing from the northeast towards the southeast can be represented by a vector. And let's do this first. I'm going to draw kind of a coordinate system here. Actually, I'm going to make this more like this. Okay, so the vector has an eastward component and a southward component. If the eastward component has a magnitude of 5. So here's kind of an important note about it, about these problems. If the direction just says east, take it as it is straight east. So going straight this way. And if it's going, let's see that our wind vector has a southward component of 15. So we're just going to go directly south. So notice that my southward vector is a lot larger than my eastward vector. That's because it's the southward component is 3 times as large. That's 15, and keep in mind this is -15 because it is south. Let's see. I want to know in what direction is the wind blowing. So if I just take a look at my answers here, they're all in this bearing form. Okay, and they have written it out like you would say it out loud, not necessarily in the way that it's written. So let's go ahead and draw my resultant vector here. Again, it goes from the origin to this final point, and I need to find what this angle is. Now, a little test taking strategy here. I'm going to look at my answers to figure out kind of what angle I need to find. And everything is saying east of south. So that means I'm going to go south first and then east. So I need to find this angle here. Now, there's a couple different ways I can do this. We're most familiar working with this triangle right here. So that's what I'm going to do. And then we're just going to do a little bit of math at the end. So I'm going to redraw this triangle. So that's 5. This is 15. There is my theta. And so I can do tangent inverse of 15 over 5. Let me plug that into my calculator. and I find out that theta say 71, we'll round that to 2 decimal places. So theta is 71.57 degrees right here. Now again, that is not the angle that I'm actually looking for. I'm looking for this green angle right here. So to find that angle, I'm going to do 90 minus 71.57 to get, well, we get 18.3 degrees, but that's just a round off error. So our answer is D. Any questions on this one here? Doesn't look like it. Let's see. So yeah, so the correct answer is D. Oh, and there's a little thing down here, but it covers up. So this question's from the 2015 pre-calculus NCFE. Only 28% of students who took this exam got this question correct. So this question is kind of more of a difficult one. Not many students got it correct, but it doesn't take that much work. Yeah, wow, it is kind of crazy. Less than a third of students got this one correct. All right, then problem 6, and this one's a no calculator one. I have worked this one out. It is quite a doozy to do with no calculator. And let's see, it is 7:38, so we are coming up on our end time here. So if you need to run out, I totally understand. If you want to hang tight so we can finish this problem, I would really appreciate it. But let's go ahead. I'm going to try and kind of get through this. I am going to draw, oh, I guess I'm drawing a green coordinate system. So I have an airplane that's headed 30 degrees west of north at a speed of 500 miles per hour. So north, east, south, and west. I'm just gonna say it's gonna be a very long vector because our magnitude is 500. And now this 30 degrees west of north, again, let's go over that. So I'm gonna go north first, and then I go in a westerly direction, 30 degrees. So then I can kind of see there is my right triangle. I'm gonna go ahead and redraw this down here. Oh, that's not a great triangle. I'm gonna redo that. There we go, that's much better. Where my hypotenuse is 500, and this angle is 30 degrees. All right, and so this is my plane. Now, this plane encounters a wind with velocity, we'll make this red, velocity of 70 miles per hour in the bearing 45 degrees east of north. So we are going this way, and this vector is much smaller because the magnitude is much smaller. There's my magnitude, 70. And this 45 degrees east of north, so again, I'm gonna go north first, and then go easterly 45 degrees. So I'm gonna draw my wind over here. All right. So this angle is 45, and my hypotenuse here is 70. So again, I'm not going to use my calculator on this. I'm going to use my knowledge of the unit circle. Solve these. I'm going to solve the plane first. So for the plane, we'll solve for our x component first. And so for this, we'll set up sine of 30 equals opposite, which is my x component, over my hypotenuse, 500. So we know that the sine of 30 is 1/2. We can solve this. This is 500 times the sine of 30, which equals x, or 500 times 1/2. I know that's 250, but for a very specific reason, I'm going to leave this as 500 over 2. We'll see why I leave it in that form in a minute. And then we are going to find our y component. So we will do the cosine of 30 is x over 500, or 500 times the cosine of 30 equals, sorry, it should be y, is y, which is going to be 500 times the square root of 3 over 2, because the cosine of 30 degrees is root 3 over 2. So my vector components for my plane are given there. Now keep in mind that we are in the second quadrant here, so my x component should be negative. Alrighty. Now I'm going to solve my wind, and I'm going to clear out this work that we did. So for my wind, again, I've got my hypotenuse of 70 and this 45. I need to find my x component. Oh, did I draw this triangle wrong? You know what? I totally did draw this triangle wrong. I am sorry, you guys. Ignore this. There we go. That's 70. This is 45, so we know that the interior angle also has to be 45, because 45 plus 45 is 90. So I need to find my y component and my x component. I'll solve my x component first. So I'll say cosine of 45 is my adjacent x over hypotenuse 70. 70 times the cosine of 45, I'm going to go ahead and replace that with root 2 over 2. So I know my x component is 70 root 2 over 2. Then my y component, I can set up sine of 45 equals y over 70. And this is a nice isosceles triangle. I'm actually going to get the same thing. So this is 70 root 2 over 2. So those are my two components. Or my components of my plane and for my wind. Get rid of this triangle too. Now, I need to find the resulting speed and bearing of the airplane. So that's basically like if I added this on here, this plane is going to push, or this wind is going to push my plane a little bit closer to being straight north. We'll find out exactly how far soon. But we're going to go ahead and add our two x components together. So I'm going to get negative 500 plus 70. Oh, that doesn't look like a 7. 70 root 2 over 2. That's why I left that as 500 over 2. That's why I didn't change it to 250, because I wanted to be able to add these really easily. So that's my x component of my resultant vector. And then my y component is kind of a little weird. 500 root 3 plus 70 root 2 over 2. So that's the component form of my plane with the wind factored in. I need to find the speed and the bearing. So to find the speed, I can do the Pythagorean theorem. And with this, you would absolutely use your calculator for it. I've gone ahead and solved it. Let me make more room here. I'm going to get rid of all this stuff over here. Let's see. So if we plug this into our calculator, I'm going to go ahead and rewrite these components in decimal form. So it should be something like negative 200.5 and 482.51. Oh wait, actually, hold on, that might not be right. I think I made that negative. Let me double check that. Nope, okay, 482. Perfect. And if I do the Pythagorean theorem with that, with those two numbers, I will find my magnitude, which is 522.51. And this is miles per hour. So this is my speed. Now speed is a scalar, it's just a magnitude, doesn't have a direction. That's why it says find their speed and the bearing. Now to find the bearing, I can do inverse tangent, and I know we're running a little bit late here, so I'm going to go ahead and say, let's see, well, let's work this one out because this one can be a little bit hard to see. So here's my x component of negative 200. Here's my y component of 482. If I do tangent inverse here, my calculator is going to give me this angle, which is not really what I want to use for bearing, but we'll go ahead and find that. So we'll say tangent inverse of my y, which is my 482.51, over my x, 205. And I find out that this angle right here is 67 point, we'll say 44. But to find the bearing, again, the bearing is this angle right here. So we'll do 90 minus that. And to get our bearing or our angle of 22.56. Now this wants it in bearing. So with this, I go north first. So that's my first letter north. And then from here, I go east or west, excuse me. So that is my bearing. So here's my speed. Here is my bearing. I have solved this problem. Now, if this problem were asking for the velocity, I would have to say both the speed and the bearing. I just put them together. All right. Any last questions on this problem here? Oh, I see some. Okay, I think I addressed those. All right, perfect. I know this was a lot. Let's see. Yep, that is all I have. So I have made some practice problems for you guys. I'll post this link in the chat in just a second. Our next seminar is going to be Tuesday, the 31st, so just Tuesday at 6:15, same time, and we're going to be going over some basic trig. Now, I know a lot of you guys kind of have seen haven't seen some of the things like polynomials and logarithms and things like that since the beginning of the year. Those are things that Math 3 covers as well. And so we've got a Math 3 seminar that you guys might want to consider attending. They're on Mondays and Wednesdays. And so their next one is Monday, March 30th at 6:15. And they'll be going over logs and interest problems. So could be a good review for you guys. Might be run a little bit differently. I forget who runs that one, but you guys might see some familiar faces pop up there. All right, and that is it. So let me go ahead. I'm going to stop sharing my screen real quick so that I can copy this link down. And actually what I'm going to do is I'm going to put the link to the folder. And this is the folder where I'm going to put all of your, all of the extra practice problems. All right, so everybody, let's just click on this link, make sure they have access to it. It should be, everybody should have access to it. And then that is it. I am going to unmute everybody now. So if anybody has any questions, they can ask them verbally. Try not to talk over each other. And then we'll be done in just a minute. All right. Any other questions?
No.
All right, perfect.
Do we just go?
Yep, if you don't have any other questions, make sure you click on the link to make sure you have access to that, and I would bookmark that to your computer, so you don't have to kind of look for that later. But then, yeah, you are good to go.
Okay, I see it. Thank
All
you.
right, we'll see you next Tuesday.
Yeah, okay.